Hola, soy Madison. What's your name? I like that part too. My favorite part was when we talked about hall thrusters. We didn't do that yet? Oh, well, let's get started. I'm a PhD student working in the Plasma Dynamics and Electric Propulsion Laboratory at the University of Michigan. We just call it PEPL. Here we work on propulsion devices that instead of using combustion to accelerate a propellant and produce thrust, we use plasma, or ionized gas made up of positively, negatively, and neutrally charged particles as a propellant. Using electric propulsion, we would be able to travel deeper into space and perform crewed missions to Mars with lots of people. We wouldn't even have to leave someone behind. But let's discuss a specific EP system known as a Hall thruster. Here is an example of a Hall effect thruster, an axisymmetric device with an anode and cathode creating an electric field. This electric field is perpendicular to an applied magnetic field. These fields are used to ionize a neutral gas like xenon or krypton, producing ions and electrons that are accelerated out of the channel to provide thrust to our spacecraft. While Hall thrusters have been researched since the 60s, there are certain concepts with these devices not well understood, such as its response to ground testing facility versus space environments. One solution is to develop models with unknown parameters that can be learned when fit to experimental data. Now that can be a bit confusing, so let's look at a well-known problem if we take Newton's apple, for instance. That's a bit excessive. Much better. If we drop an object, in this case our apple, from a position at rest, the object will increase in speed as it descends until it reaches the ground. We can measure the height relative to the ground as it descends with respect to time and record these values as our experimental data. When we plot this, we see that the trend looks like a parabola, which has a known form, or just using kinematic equations, we can identify a model. We can fit this model with tunable parameters. The parameters A and H naught can be changed until the model closely fits the experimental data. So we now have actual values for these terms because we calibrated to measure data. Interestingly enough, the A term represents acceleration with magnitude of 9.8 meters per second squared. This term is, of course, acceleration due to Earth's gravity at sea level. So we were able to back out this well-known value by fitting a model to data. We gained a better understanding of the physics of this system using this method. While gravity is a more involved concept, we still determined that the acceleration term from our kinematic equation is due to the force of gravity on Earth. Now we can also apply this for behaviors of Hall thrusters by taking experimental data, measuring in this case ion current density at various angles across the front of our thruster, or rather in our plasma plume. We can fit a model with parameters that we learned similarly to our A and H naught. If we change the back pressure during our experimental tests, the thruster performs differently. Thus, we can improve our understanding of how the plume is affected by variables like background pressure in our testing facility by fitting the current density data to a model. We can also apply this to electron transport in our thruster channel and how it can affect our ion velocity as well. We can measure these velocity profiles and fit models dependent on things like the number of electron collisions in the channel and learn the associated parameters. We can also determine how electron transport can relate to back pressure or thruster power as well. My work specifically focuses on the fact that typically a lot of data is needed to have a good model fit. This can be challenging for testing and fitting computational. Ow. I try to determine at what positions in the plume or thruster conditions to measure are most informative for training a model, so that we use a small amount of data and get the same model fit as if the larger experiment were performed. For ion velocity measurements, a physical probe cannot be inserted into the plasma plume without affecting it. Instead, a laser is pointed to the thruster channel to measure the profiles. This method is known as laser-induced fluorescence. This diagnostic can be very expensive to perform, so a smaller optimal dataset is extremely helpful during experiments. This dataset is found using a method known as optimal experimental design. This framework can be applied to various Hall thruster models, making thruster testing much easier with regards to time and thruster or probe health, for instance. Now, if you would like to learn more about electric propulsion, feel free to check out our website and see more great videos of my lab mates explaining their research on our channel. Thanks for watching.